Hello, welcome. In this short video, let us look at the maximum likelihood estimator of the parameter A in a linear model where the noise has a Gaussian distribution with a covariance matrix C. So consider the linear model X equal to A times the vector 1 plus the noise vector W, where the vector 1 is given by basically n ones. And the vector W has n components, that is W of 0, W of 1 up to W of n minus 1. So this is the noise vector and this is the vector 1 and this is the observation vector. So the model for noise vector is a multivariate Gaussian distribution with the mean equal to 0 vector, and the variance is the covariance matrix is given by the matrix C. So as a result, the probabilistic model for the observation vector X is a multivariate Gaussian distribution N with a mean equal to A times 1 bar, that is the vector 1, and the covariance equal to the matrix C. So given this probabilistic model, we want to derive the maximum likelihood estimator for the parameter A and prove its efficiency. So the maximum likelihood estimator can be determined by optimizing or maximizing the log likelihood function. The log likelihood function L of x with the parameter A is defined as logarithm of the probability distribution of the vector x, which is equal to log of 1 by 2 pi power n by 2 1 by square root of the determinant of the matrix C and exponential of minus 1 by 2 x minus a 1 bar transpose C inverse x minus a 1 bar. So this is the multivariate Gaussian distribution, and upon simplification this becomes minus n by 2 log of 2 pi minus 1 by 2 log of the determinant of C, the matrix C, and minus 1 by 2 x minus a 1 bar transpose C inverse x minus a 1 bar. Now by equating the first derivative of this log likelihood function with respect to the parameter A equal to 0, we can basically derive the maximum likelihood estimator for A. That is, the first derivative of the log likelihood function is clearly the first term and the second term have derivatives equal to 0, and the third term has the derivative of the third term is minus 1 by 2 derivative of this product, which is the derivative of x transpose x transpose C inverse x minus x transpose C inverse a into 1 bar minus a 1 bar transpose C inverse x plus a square 1 bar transpose C inverse 1 bar is equal to 0. This implies the derivative of the first term is 0 and the second term, the third term the derivatives of the second and third term are minus x transpose C inverse 1 bar and which is also same as the derivative of the third term, which is 1 bar transpose C inverse x. The last one is 2 times a times 1 bar transpose C inverse 1 bar, which is equal to 0. Therefore, the estimator A hat is equal to the sum of these two terms divided by this product. Of course, this is 1 by 2 1 bar transpose C inverse x plus x transpose C inverse 1 bar divided by the product 1 bar transpose C inverse 1 bar. Therefore, the maximum likelihood estimator MLE, the parameter A, is, since these two terms are equal, we can rewrite it as 1 bar transpose C inverse x divided by 1 bar transpose C inverse 1 bar. Clearly, we can notice that when the covariance matrix C is equal to sigma square multiplied by the identity matrix identity matrix n I with the number of terms equal to n, that is, okay, clearly when C equal to a diagonal matrix with this constant variance, we have sigma C equal to sigma square times the identity matrix In. We have the MLE estimator, that is maximum likelihood estimator of the parameter A, is equal to 1 bar transpose C inverse becomes 1 by sigma square into I inverse into X divided by 1 bar transpose 1 by sigma square I inverse, which is also again I, into 1 bar, which is clearly equal to, the sigma squares basically cancel each other, and we have 1 bar transpose multiplied by x, which is clearly the sum of all the values in the vector x, that is summation n equal to 0 to n minus 1 x of n. And in the denominator we have 1 bar transpose multiplied by 1 bar, which is basically the sum of n ones, which is n. Therefore, this is the arithmetic average of the observations in the vector x. This formula basically gives the general expression for the parameter A, or the estimator of the parameter A. So this is a special case for C equal to a diagonal matrix with constant variance. Diagonal covariance, which basically means that W of n are IIDs. So in that case, the maximum likelihood estimator of the constant A is nothing but the arithmetic mean or sample average. Now let us look at the properties of the maximum likelihood estimator. That is, we want to calculate the variance of the estimator A hat, which is defined as expectation of A hat squared minus square of the estimator, expectation of the estimator A hat. So the expectation of A hat is clearly equal to expectation of, we basically use this formula, 1 bar transpose C inverse x divided by 1 bar transpose C inverse 1 bar. We write this factor outside because it is in a deterministic value. So we have 1 bar transpose C inverse expectation of x divided by 1 bar transpose C inverse 1 bar. And since the expectation of x is equal to A times 1 bar, this can be rewritten as 1 bar transpose C inverse A times 1 bar divided by 1 bar transpose C inverse 1 bar, which is clearly equal to A. Therefore, expectation of A hat is equal to A, and therefore A hat is a unbiased estimator. Now let us look at its second moment, that is expectation of A hat squared, which is equal to expectation of 1 bar transpose C inverse x whole square divided by 1 bar transpose C inverse 1 bar whole squared. Since the denominator is a deterministic value, we can take it outside the expectation. So we have 1 bar transpose C inverse 1 bar whole square, expectation of 1 bar transpose C inverse x whole square. So this can be written as 1 bar transpose C inverse 1 bar whole square, that is the denominator. Then the numerator becomes 1 bar transpose C inverse expectation of x into x transpose multiplied by C inverse into 1 bar. Now we use the definition of the covariance matrix C, which is given by expectation of x into x transpose minus the product of the means of vectors x, that is expectation of x into expectation of x transpose, which is clearly equal to expectation of x into x transpose, that is the second moment, minus the mean is defined by A into 1 bar, and the transpose is 1 bar transpose into A. Therefore, expectation of x into x transpose, that is the second moment of the vector x, is C plus A squared into 1 bar transpose. So by replacing or by plugging in this value in the previous expression, we have expectation of A hat squared is equal to 1 by 1 bar transpose C inverse 1 bar squared multiplied by 1 bar transpose C inverse multiplied by C plus A square 1 bar into 1 bar transpose. Of course, multiplied by C inverse into 1 bar. This becomes 1 by 1 bar into 1 bar transpose into C inverse into 1 bar squared 1 bar transpose C inverse C into C inverse into 1 bar plus A squared into 1 bar transpose C inverse into 1 bar whole squared. Clearly, this is equal to 1 by 1 bar transpose into C inverse into 1 bar, because the first term reduces to 1 bar transpose into C inverse into 1 bar, and one of the terms cancel with the one term in the denominator. So you are left with 1 by the product 1 bar transpose into C inverse into 1 bar. And the second term basically becomes A square, because these two factors cancel each other, this one and the denominator. So the variance of the estimator A hat is equal to 1 by 1 bar transpose C inverse 1 bar plus A square, and we subtract the square of the expectation, which is again A. So we have minus A square. Therefore, the variance of the maximal likelihood estimator A hat is equal to 1 bar transpose C inverse 1 bar. Now from a previous video, we derived that the variance of the estimator A hat for a linear model A into 1 bar plus W is given by 1 bar transpose C inverse 1 bar. Therefore, and in this video we clearly derived that the variance is actually equal to 1 by the or actually equal to inverse of the product 1 bar transpose C inverse 1 bar. Therefore, variance of the estimator A hat for the maximum likelihood estimator is equal to the CRB, which is 1 by 1 bar transpose C inverse 1 bar. Therefore, maximum likelihood estimator for the parameter A in the linear model x equal to 1 bar A 1 bar plus W is the efficient estimator since it reaches the CRB. Thanks for watching.